you know,
Yeah, sorry, I started
oh
recording.
yeah. The start of this is you know, uh, what is a mathematical representation of a program, right? So, there are many ways to be able to start this, but if you think about it from a math perspective, the simplest thing that you can do is you can just say, a program is really just an object, which is, f of x, some input, which is really just some, f n O circle. Let's see. No, that's too big of a circle. Trying to remember the compose. Um,
Is that Cirque?
oh, circ. Yeah. Okay.
Yeah.
Circ f n minus one circ l dots. Circ f1. So really, what you can think about as a program, right? It's like you do the first thing, you do the second thing, you do the third thing, right? So a representation of a program is really just a composition of a bunch of functions at the end of the day, right? Now there is two kind of branches there, right? So there are two major there are two major types of programs, though. There's static and there's dynamic, right? And so the key difference is static is, the decomposition of f is independent of the input, versus the decomposition of f is dependent on the input, right? So what do I mean by that? So we have we think about a program as it's some kind of y equals f of x, right? Now it might be x might be a string, it might be an integer, right? In the expanded space of programs, it's x doesn't necessarily need to be, a real number or whatnot, but every function that you write on a computer is a function kind of like this, right? Now, when you think about, what types of programs that you have, the two major types of programs are either static graphs or dynamic graphs. And what a static graph means is that the actual computation is the same for no matter what input you're putting in there, right? And so for that kind of case, it's fairly straightforward, right? So for that kind of case, you just write down the decomposition, and you have a compute graph. And I know that Raphael did a little bit of the compute graph version of automatic differentiation. You just do automatic differentiation on the compute graph, and that's equivalent to differentiating the program, right? But the key issue is that many programs are dynamic in nature, right? So example is an if statement, right? I'm not going to write down a full if statement in LaTeX really quickly here, but I'm just going to do something like, if x is less than 1, then, x squared, otherwise, cosine of x, right? This is a function that can show up inside of a program, but notably, it is dependent on the value of x, right? So if x is less than 1, then runs one function. If x is greater than 1, it runs a different function, right? So this decomposition here will change depending on it will change depending on your input, right? And so one key question with differentiable programming is, how do you differentiate dynamic programs that come from, real scientific applications, right? So first of all, let's motivate this question a little bit. What is a real scientific application that can have a dynamic program, right? There's actually a fairly simple one, right? So one simple example to start with is Newton's method, right? So Newton's method is, f of x, p equals to 0, or let's do, yeah, so let's do f of x p equal to 0, where, x is the thing we are trying to minimize, and p is some set of parameters, right? So for the example, we have something like, x squared minus p, x squared minus p is equal to 0, right? Solve for x, right? So this is a parameterized root finding function, right? If I change p, I change the solution for what x should be. And how you would solve this is via Newton's method, right? And very quickly here, right? What is Newton's method? Well, Newton's method is x and n plus 1 equals x of n minus minus g, or let me call it g, yeah, g of x divided by divided by g prime of x, right? But the way that you'd actually write this, and if you have a non-scalar case, right? So I'm going to write it in the vector form. It's going to be this g prime of x inverse, right? So it's this Jacobian inverse multiplied by the function evaluation. This is done at n. Doesn't need to be, but that's a technical detail. So this is a classic Newton's method, but written instead of dividing by the derivative, I'm multiplying by its inverse, left multiplying, because this is the generalization that works for vectors and matrices as well. So this is Newton's method, right? But when you actually write Newton's method as a program, you normally would do something like for I in 1 through n. Well, if you do that, you have a static graph, right? So if you say, I'm going to do n iterations of Newton's method, then the calculation to get the 0 is constant. But generally in practice, you don't do that, right? What you say is while the tolerance, or while the error is greater than, some tolerance, right? So what is the error in Newton steps? Well, this is where I'm defining, define g of x equal to x squared minus p, right? We know that we will have solved the problem when g of x equals 0. So g of x is the error function, right? So you can think about it in a few different ways, but let me kind of go back through this, right? So this is Newton's method, right? We want to solve for the x that gives us x squared minus p equals 0, right? And so we define this g of x, and Newton's method says if you do this enough times, you will get your 0, right? And every single point you can check, and you say, okay, g of x is it, how close is it to 0? Okay, it's 1 times 10 to the minus 9. That's close enough, and you stop, right? So for some values, for some inputs, you might run 5 iterations in Newton's method. For other inputs, you might run 10 iterations in Newton's method, right? So what we want to do then is we want to be able to come up with a way of saying, this is a valid program, but it doesn't have a constant computation graph. Are there things that we can do to be able to calculate the derivative of these kinds of operations? So, if you do have a Newton method inside of a code, for example, if you have a PDE solver and you want to differentiate the PDE solver with respect to parameters, right? This is the kind of exact problem that would show up in there, because you would have a Newton's method for your nonlinear PDE solve. And so therefore you need to differentiating the PDE solution is equivalent to this exact problem of differentiating a Newton method, right? So how do you go about doing this, right? There's a few different ways. In my lecture notes, I describe it in what I would say is like the classical way of doing the derivation, but I have a much simpler derivation that I like to use these days, right? So first of all, simple derivation, using concepts from last lecture under assumptions of what your last lecture was, right? So recall that forward mode automatic differentiation is defined by Jacobian vector products, right? So forward mode AD is defined by doing so. So let's say we have a program. Let's say we have this program, right? Or then forward mode AD. Well, the way that we compute this is we say, okay, mathematically the Jacobian, right? So the Jacobian of this function is equal to the Jacobian matrix of the nth one multiplied by the Jacobian matrix of the n minus one, right? And then L dots, J1, right? So this is just a mathematical relationship. So if you have the composition of a bunch of functions, right, and you take the derivative, right, so the Jacobian matrix, so here I'm just using that as a stand-in for f prime, right? The Jacobian matrix of the composition of functions is the multiplication of the Jacobian matrices. That's something that just falls right out of the chain rule. So that's just like one of these matrix calculus rules, right? And now forward mode AD is the computation of the following object. So it's J times V equals Jn minus one L dots J1 V. Where what you do is you just put your parentheses here, and then if you have J2, you put your parentheses here, right? And so it's successive Jacobian vector products in order to compute the full Jacobian vector product of the program in a step-by-step way, right? Which I presume this is what was kind of described in the previous lecture, right? And then of course you have reverse mode automatic differentiation. So reverse mode automatic differentiation is instead defined by J. Well, so if you do J, there's a few different ways to write it, but if we say we want to calculate J transpose V, this would be equal to this object here, right? So this object here, transpose, this object here, transposed times V, which if you see is equivalent to then, well, how do you take the transpose? Well, the transpose of a composition of operators actually reverses the direction, right? So you'd have then J1, J2, L dots, Jn minus one, JV, all with the transpose on there.
So
right.
in class we did just the vector Jacobian product, but it's here we just take the transpose, right? So that it's always multiplying by v to the right. But yeah, we did left to right and right to left. So reverse was left to right, and forward was right to left.
Yeah. So that's what I mean. There's two different ways to write it. You can also write it like this, right? Where you have the VT, your vector transpose. So you have a row vector, which is then computed.
Without the transpose. Yeah, that's right. Yeah, that's what we saw. But it's the same thing. It's just the transpose of this.
Yeah. So it's whichever way you want to transpose it. I mean, the two derivations are exactly the same. But the key is one is doing successive Jacobian vector products through a program step by step, and then you define what is the Jacobian vector product of the plus operation, what's the Jacobian vector product of the cosine operation, etc. And that gives you forward mode AD, right? Reverse mode AD is the same exact operation, but you first solve forwards and then you pull back a vector, right, that doing these vector Jacobian products at each step of the way, right? So that's so that gives you an idea that if we can write down a program, then we can do forward and reverse mode AD to be able to compute these objects, right? So now let's go back to this Newton problem, right? So we have this object, right? For infinite n. How do we compute the derivative of the solution with respect to p, right? So to kind of maybe make things a bit actually. So remember that g here has this p inside of the definition, right? It's a parameterized function. So how do we compute the derivative with respect to p? Well, here's where would you get started? Well, let's say you actually wrote down a Newton's method, right? So if you wrote down a Newton's method, so you'd say, okay, here's my initial condition, and now I run Newton's method for n iterations, I end up and I got the zero, right? Now, how do you choose that initial condition? Well, I mean, as long as the initial condition is sufficiently close to the root, then it will work, right? Now, if you think about this, like the root given the x0 comma p, like the solution object of this, right? So if you think about that, if you say that this is the function that is the solution to Newton's method, right? If we say that this is the function that is the solution to Newton's method, what we want is the fraction d root of x0 p dp, right? This is what we want to calculate, right? That how the root of Newton's method changes, not the initial point or not the x's in the middle. We want to get the end point. And the key here, though, is that if you think about it, with Newton's method, well, if I start Newton's method here, I move and I go to the zero, right? So there's kind of this basin where if I start Newton's method here, I go to the zero. If I start Newton's method here, I go to the zero, right? And so actually, if I start Newton's method anywhere, if I keep on hitting the same zero, as long as I'm in this basin of attraction, it does not change my root, right? So notice that you do have the relationship that d root of x0 p d x0 is equal to zero, right? Because it doesn't actually matter where you start your Newton's method. You're still going to get a root. So there's a trick then that comes into play. So this is technically Newton's method technically has a dynamic computation graph, right? You don't know how many steps it's going to take to get to the root. But does anyone see the trick that would make it so that way we can differentiate a static graph and get the solution? I would say that this fact that the derivative is independent of the initial condition is a fact to use there. I want to pause for a second.
And we had a related question: is the root of Newton's method x0, or is it something else? No, it's something else. X0 is your starting point, and then you
Yeah,
do your
yeah,
iterations until you converge to the root.
yeah.
So
Root of x0 p is equal to x infinity, right? Oh, I guess, oops, x empty, yeah. Right, where it's done by doing this infinitely many times, right? But now in practice, your computer program will stop at like x sub 6 or x sub 7, right? You don't quite know where it's going to end. So mathematically, it's defined as if you run Newton's method forever, but your computer program will not run it forever, right? So this is the kind of tricky issue for computing the derivative, right? You don't want to compute the derivative. Technically, Newton's method is the infinite composition of functions, and that's pretty hard to write down the derivative of. So okay, so we want to take the derivative of the solution to Newton's method, but we don't care where we start. So anyone see a trick here? The trick comes from we can choose a starting point. So what's a nice starting point for Newton's method?
Would it be zeros so that maybe things would cancel out?
Exactly. So since the solution does not depend on the starting point, choose x sub 0 equal to x infinity, right? Make it be the root. And so if you do that, then in one step of Newton's method, you get the solution, right? So what you can then say is that x empty, right? So this is a relationship that just holds true. this is a relationship that holds true. It has to be true for Newton's method, right? That at the root you have a fixed point, right? So this is then just another way of writing root of p, right? The root with respect to, now I don't need to write x0 if I'm choosing x0 to be x infinity, right? This is now the function, the root of p. To compute it, you just compute this function right here, right? And so now I can take now with this, I have just one iteration of Newton's method, right? I have a static compute graph, right? And so with this, then I can say, well, so how do I compute this, right? So let's do our steps here. So first of all, what you do is you would calculate y equals g of x infinity, right? And then you compute, then you would compute g inverse y. Well, I'm just kind of giving names to things like a computer program, right? But you wouldn't actually compute it like this. What you would do inside of a computer is you would say, okay, I'm moving this to this other side, right? So you compute z like this. And then how would you actually do that in your computer? Well, you'd say that z equals gx backslash y, right? So remember, you never compute matrix inverses. You always do an LU factorization. I'll skip over the step, but if anyone has a question there, that's always a kind of fundamental thing. So you always compute with the LU factorizations whenever you can, right? And then output is equal to x empty minus z, right? So then all you'd have to do is, if you'd have to just say, okay, this is now a static compute graph. Now there's kind of complicated pieces in here, right? So so this is a matrix that I then have to do the LU factorization of and such. But now if I can take the Jacobian vector product of each of these stages of the program, then I can do reverse mode AD. So so what does that actually look like then? All right, so you have y equals okay, so you first compute all the objects going forwards, right? And then as you go backwards, what you would do is you say, what is the Jacobian of the last statement with respect to p? Well, p doesn't show up in this equation at all, so it's 0, right? What's the Jacobian of the z statement with respect to p? Well, it would be the derivative of this with respect to p. So the derivative of this with respect to p with respect to p is equal to, well, this is a constant, right? So I can, y is a constant with respect to p in that line. So I can say it's here. So there you would have and so, I mean, if you remember all the steps of the computation graph thing, right? So you basically just say that this is now the dg of x empty, well, the derivative of the Jacobian with respect to x empty dp, right? Let me actually write it down in this example, right? So in our example here, where was it? Right. In our example here, we had g prime, g of x. So g prime with respect to x would actually just be 2x. And so then here, fraction dg prime of x empty, or g prime of x dp would just be equal to 0, right? It would be non-zero if you actually multiplied here or had a nonlinear function, right? In this case, it ends up 0. But so, you can calculate the derivative here with respect to p. And then, you take, so what you would do then is you would say, okay, you compute forwards, and then you define your pullback vector 1, and you multiply it. You take the Jacobian here, transpose it. Well, Jacobian here is 0, transpose it 0, pull back. Jacobian here is 1, pull back, and so your gradient calculation here would just end up being 1, right? So
we had the question why is y constant? So you can take it out of the derivative in the solve.
Oh, so constant with respect to that step, right? So it's constant with the partial derivative of this function with respect to p is 0, right? So I'd say go back to the computation graph piece, right? The point about the computation graph is that when you decompose your functions, right? When you decompose your functions, you can think about every single function as I'm only looking at the relationships of this specific stage. And for this specific stage, y is just the value y, and then this is the function g applied to x. And so g actually has parameters in here, right? So, at this stage, at the stage before it, it is not the way that you compute y is dependent on parameters, but here the value y is not dependent on parameters, right? It's just, yeah.
And we had another question of like, how would you know x infinity? So here we're talking about how to compute the gradient. So we did already the forward pass. So so we solved for x infinity, and y is some value that is on the computer. Is that correct?
Yeah. So in summary, what does this tell us about computing the derivative of a Newton method with respect to its parameters of its function, right? So here are the steps, right? So step 1 is solve solve for root of x0 p with any x0, right? So that's the first step. So the first step is you just run Newton's method, right? And this gives you x infinity, right? And this is kind of key to anything that you do with the derivatives. You always have to have the primal pass. So whatever you're trying to differentiate in differential programming, you're always going to run the original program. Now, the key thing here is like once you have x infinity, right? Run reverse mode on the 3 operations above, right? So you do reverse mode AD on these 3 operations above using the same kind of thing that you talked about before with how do you do the compute graph and all that, right? I mean, it takes forever to actually do the full compute graph discussion, so I'm gonna kind of hopefully enough of that was done, right? So but that's the key steps here, right? And so is the interesting thing here, right? Is so interesting fact is that it may have taken 40 steps of Newton's method to go forwards, but it still only takes 1 step to go backwards, right? And it seems a little bit weird at first, but if you actually think about it, this ends up being equivalent to the implicit function theorem. So I'm gonna switch over screens here to the lecture notes I give, right? So in the lecture notes I give, I actually do the derivation a completely different way using the implicit function theorem, right? So using the implicit function theorem, what we say is, if we want to solve f of x comma p equal to 0, what we can do is we can differentiate the solution of Newton's method at the root by p, right? And if you then move things aside, solve, you get that the derivative of the solution with respect to p is computed like this, right? Which, if you notice, if you actually look back at the equations that we've written down, right, this is the inverse Jacobian that shows up from Newton's method, and this is then just the derivative of the g, so that y term with respect to p. So it's exactly the same as the 1 step of the Newton's method. And so if you then have a loss function, right? So if you have, for example, a cost function like defined by the output of the Newton's method, right? So g is a function that takes in the output of the Newton's method. The derivative of this cost function defined on the Newton method solution is well, you just differentiate it with respect to P. Like where did I write the, yeah. Maybe it didn't write the loss function the best way. You take its derivative with respect to P, and you'll notice that then that the derivative of G, which is output of Newton's method with respect to P, is going to be given like this. And you can see that you have exactly this term in here that comes from the one step of the Newton's method. So this uses a different approach to do the derivation. And we'll go over this kind of approach when we go into the ODE part. But you'll want to, you might want to look at these notes as a different way. But I do kind of just like this other way of thinking about the derivation of Newton's method, because in this way to think about it, right, something that is fairly non-intuitive has kind of popped out at us, which is that in this case, if we think about this differentiation, the way that we do the differentiation in the reverse pass is not necessarily the differentiation of the code that is ran, because if you think about the code, you might run the code 30 steps in Newton's method. You could at that point say that is the computation graph that I use to compute my output, and I compute back going 30 steps of Newton's method. But using this relationship that we know has to be true about the root of the equation, you can also say, well, I can always use one step to go backwards. In fact, this is a fact that's true about any iterative method. So any method that iterates to a solution, that is like decreasing tolerance. So complementarity solvers, nonlinear optimization, the derivative of those kinds of functions, these implicit functions, can actually always be given as one step using a very similar kind of proof. So this gives you something, so this is why I titled this, from automatic differentiation to differentiable programming. There's something that goes non-trivial when you start to differentiate programs that come from mathematical objects, right? This is a fairly non-trivial fact. If you just do automatic differentiation on your code, right, it will not do this. It will say, I will solve forward 30 times and I'll pull back 30 times. But that pullback is the most expensive operation. And so to actually to actually take the derivative of the Newton's method inside of a PDE solver effectively, you will actually want to tell it, no, compute this derivative in this special way.
And that's true for any iterative method. So that's why it's useful. And well, Newton methods, like one of the questions was like, do you know if it always converges? Actually, it does not always converge Newton's method, but like it's true. Yeah. This reasoning is like once you have a solution that you can run it backward, right? Like your computer might run forever and never find X infinity. But if you have X infinity, then you can run it backward by using X infinity.
So the way to describe it is there's a basis of attraction around the root, right? So there's an open set. Root.
So if you're there, if you're there, it converges.
So for anything in that basin of attraction, it converges. And so because it converges for everything in that basin of attraction, if you take any x0 from the basis of attraction, you get the same output from Newton's method. And so, so you probably want to maybe go back and actually formalize this step that, oh, hey, the derivative here with respect to x0 is equal to 0, right? This is, in formal language, it's like take any x0 from the basis of attraction, but so you do have to restrict the x zeros that you're looking at there to the ones that are converged, but you can have guaranteed set that always converges from. Yep. So okay, so oops. Did I lose my screen share? Okay. Those are iterative methods, and they have a very nice property, right? So what's another case where automatic differentiation has interesting changes when going to differentiable programming, right? So another case is the differentiation of ODE solvers, right? So first of all, as a quick kind of primer, an ODE is an equation, f of u equals f of u comma, or u prime equals f of u comma t, right? So a classic example would be something like u prime equals usually I use alpha, but I'll just say PU here, right? So this is the linear ODE, right? And its solution is U of t equals the U of 0, the exponential of PT, yeah. Right. So the way that you do this, right, is remember you just do du dt equals pu, and then what you do is you move this over, right? This is kind of funky algebra. That's not quite true, but this is like the general derivation that people do, right? You move this over, and then you integrate both sides. You integrate both sides, and now what you have is log of u equals to pt, and then you exponentiate both sides, and you have u equals, exponential of pt. Well, this is plus a constant, right? So plus a constant, and that's why you have multiplied by a constant, right? Because that's just adding the exponential, and this constant you can just solve for ends up being u0, right? So that's how you get the solution for the linear ODE, right? So the reason why I write this down is showing this is because if you think about it, you have software that solves ODEs, right? ODE 4.5 and MATLAB, and you have Julia, Civ5, and etc. Right? So you have all this software that does it, and they're effectively functions, right? They are effectively functions, right? They take in u0. They take in u0. They take in what is your initial time, what is your final time, and what are your parameters, and they spit out this u of t representation, like an array of time points for the solution at all points in time, right? And so and they're used all the time in mathematical models, right? So many mathematical models are defined by ODEs. And so, just to write down a few, you have chemical reaction equations, physical equations, right? Anything like relativity, robotics, right? Like everything is written in differential equations, like 3, 4, like you've probably seen a billion differential equations, right? And so the key here is we might want to differentiate the solution of the ODE with respect to the parameters, right? And why might we want to do that? Well, for example, if you're trying to make your ODE solution fit data, well, then you want to do something like gradient descent, where your program is calculating the solution of an ODE, and you want to take the gradient through that and move your parameters until the solution to your ODE goes through your data, right? And so that's like a common way to do parameter calibration, and that requires calculating the derivative of the ODE solution with respect to parameters. And so, okay, so how might you do that? Well, it is just a function with respect to parameters. It's also a function with respect to T0 and TF in your initial condition. And so what we want to do then is find out how to differentiate this thing with respect to P. Now, if you just look at the linear case fairly quickly, right? So this is this here, right? So if you want to take the derivative, d u of t dp, right? Well, the first thing that you should note is that the derivative of u of t is actually a function of time. It itself is a function of time, right? At every single time point, so hopefully the board is visible enough here, right? If you have an ODE solution, right? You have an ODE solution over time. So this is t, this is u. If you change your parameters, you will have changed to a new function, u of p star t versus u of pt, right? You will have moved your function, but how much you've moved your function will have changed at different points, right? So as you go further and further along, there's actually exponential growth in the linear ODE, and so there's also an exponential change that your p has caused. And so the derivative in the solution is actually not just a function of P, but it's also, you have to say, what time point am I looking at? Every point in time has a different derivative associated with it with respect to changing your parameters, right? And so if you differentiate this, right, you can work it out here. This is just, ddp of this, which is then going to be equal to, P and then this same expression, right? But that should be fairly non-obvious, right? Because here we, if I just told you, if I just told you, u prime, so let's just write these things together. U prime equals, pu. So that's because we have multiple derivatives here, let me now actually just write it as, du dt, right? So the derivative in time is just simple pu, but if I write down now the derivative with respect to p, right, you say, okay, well, the derivative with respect to p is this entire function right here, right? You saw the whole derivation. The derivation is not hard, but this tells you that actually finding out what the size of these arrows for the change is something that's fairly non-trivial, right? And this required here that I knew the analytical solution to the ODE. Almost all ODEs do not actually have an analytical solution that you can write down. You can prove that most ODEs do not have an analytical solution that can be written down. So you can't even do this by hand. So you have to have a computer program compute what this thing is. And so how do you actually take the derivative of this, right? So let's look at the different ways to do AD, but now on this continuous space, right? So let's start with forward mode AD, right? So let's start here. So you have u prime equals f of upt. So and I say that I have a program that can compute the solution to ODEs, right? So how can I get the derivative of the solution to an ODE with respect to P, given only the fact that I have a program that can compute solutions of ODEs? Well, on this ODE expression, let's take the derivative with respect to P, right? Now, if I do this, what I have is, ddp or ddp of, du dt equals fraction df dp, which if I write this out, this is going to be fraction partial f partial, let's see, that is going to be, yeah, and then that's going to be du dp, right, plus fraction partial f partial p, right? Yeah, so this is just the extended chain rule. But now here's the thing, right? So what we want is fraction du dp. So let's just exchange, right? So in a formal math class setting, I'll say, okay, you have to make sure that your solution is sufficiently nice. So your solution has to be at least differentiable, et cetera, right? But under the right conditions, we can then switch the limits, right? So you can go back under what conditions can you switch these limits? Well, defined by the integral, et cetera, but that's for the analysis class, right? So you have to prove that the solution has the right properties such that swapping limits works. But if you swap your limits, then
it's called, for those interested, it's called the dominated convergence theorem.
Yeah. So your real analysis course will go into that. But here though, what we actually want to compute is this thing, right? So if we call this S, right? So a lot of people call it the sensitivity. I like writing it like this because then it becomes more clear, right? But then, this is ddt of S. So this is S prime. And wait a second, right? This is an ODE. So let's actually write it down here. So you have u prime equals f of upt, and you have S prime equals S prime equals this, right? Where, well, this is using the partial derivative of f with respect to u, but you know how to compute the partial derivative with respect to u because that's the first ODE, right? So now you have this is a system of two ODEs, right? Or two components, right? S, U, and S, which if solved together, the S equals fraction du of t dp, right? And so, and notice that S is actually, it's an ODE solution, right? So it's a function of time. Every point in time for S is the derivative of the first ODE with respect to parameters. So how do you solve this? Well, I don't remember. All I have is an ODE solver. I can't write down analytical solutions to this thing. But what I've done with differentiation is I found that there is this new ODE where if I plug this, if I plug this new ODE into my ODE solver, it gives me the derivative of the original ODE as the solution from this ODE, right? And so this is then a kind of a similar kind of trick in differential programming. So if you look in a lot of these cases, you either tend to have cases like the Newton's method where there's iteration to zero and you can then kind of say, well, I can chop off most of the computation. Or what ends up happening is the derivative of your original program ends up being able to be calculated by running that same kind of solver on a new input to that same program, right? So the derivative of an ODE is an ODE. The derivative of a delay differential equation is actually a delay differential equation. The derivative to an LU factorization or the derivative of an SVD factorization is an SVD factorization, right? So it's kind of this funny relationship that you see show up a lot of places. But this is then the key, though. I don't need if all I have is an ODE solver, I can use the ODE solver to solve this ODE and get my derivatives without ever having to know how to compute the analytical solution. So this is the forward mode way. So this is known as the forward sensitivity equations. And the reason why you can understand it as forward, right, is this piece right here, right? This piece right here is a familiar object, right? Familiar object. This right here is the Jacobian of the forward equation multiplied by a vector. Right. So if you think about it, right, if you think about it back in this form, right, this is basically what we did, right? So let me put these two side by side here. Right, you have an ODE solver where what the ODE solver, if you think about like Euler's method, right? So Euler's method for solving ODEs, right? What you would do is you'd say, du dt equals f of u pt. Instead of using, well, let's now move this over, dt, right? And instead of using infinitesimal steps, what you do is you just say, I make this a delta, or I make this a delta, make this a delta, right? And delta u is equal to u sub n plus 1 minus u sub n, right? And so Euler's method then can then be written as u of n plus is u of n plus delta t f, right? So this is your classic Euler's method, right? Where you take your current point, you multiply it, and then you take you take your current point, right? Take your current point, you take your derivative, you walk your derivative over by delta t, and there you go. Because that's the basic definition of the derivative is it's a linear approximation. So just follow that line for a little bit, and then take a new derivative, follow that line for a little bit, right? This is Euler's method, right? And so in going forwards in time, what we're doing is we calculate f. And then we jump to the next point. We calculate f, we jump to the next point. We calculate f, we jump to the next point, right? It turns out then that what the derivative of this, what the derivative of this ODE solver is effectively doing is, well, you calculate the, not f now when you're calculating derivative, but you do the Jacobian you take the Jacobian of it and you multiply it to a vector, and then you take the Jacobian of it, you multiply it by to a vector, right? And so effectively, if this is solving the ODE forwards, this is doing the same exact thing, except doing just this Jacobian vector product at every step of this ODE. It's just doing this relationship right here simultaneously to the other form. Just this is now just writing that operation in continuous time, right? So here, it's step by step. It's, oh, I do F, I do F, I do F. So therefore I do Jacobian of F, then multiply by a vector, Jacobian of F multiplied by a vector. But if you then send delta T back down to 0, then the derivative in time is you multiply a Jacobian by the vector. So it is just the continuous operation, the infinitesimal limit of doing Jacobian vector multiplies of this operation. So it is that nice generalization. Now, how much more time do I have though?
About 20 minutes. About 20
Okay.
minutes.
So that's hopefully enough time to do a bit of the adjoint. So this is then clearly the continuous version of the forward mode automatic differentiation, right? So if we want to kind of compute the derivative of a continuous function, we can do that by solving an ODE of a continuous function where that ODE is given by Jacobian vector multiplies, right? And so what is the reverse mode way of taking the derivative of an ODE solver, right? So there's many different ways to come at the solution. I would suggest watching the video that comes with the SciML lecture notes if you want to go through the classic derivation. I won't have time for the full classic derivation, so I'm not even going to try in this time. But you can watch the full hour if you're interested in like the full step by step with integration by parts and everything. But
that's lecture 11, right? In your yeah, I'll share it on Canvas.
Yeah, but this actually gives you this, well, if this is our ODE solver, right? Then the way that we compute forwards is by doing this function, right? And then so after we've computed going forwards, right? Then we want to do reversing of this computation graph, in which case what we would do is we would do the vector Jacobian, then reversing would be the Jacobian vector transpose products, right? You'd be doing these Jacobian vector transpose Jacobian products going backwards at every step of the operation. If you take that to its limit, what you get is, right? If you take that to its limit, what you get is a relationship where you say lambda transpose that, and then you basically have the same extra term show up here. So because you can have the partial term, but essentially if you go forwards with Euler's method, you reverse with Euler's method, but then you divide by delta t, send t to equal to 0. You see that you're actually solving an ODE. So and so what is the adjoint or reverse mode of an ODE? It's solving two ODEs, right? And the process goes like this. Step one, you solve u prime equals f of upt, going forwards from your initial condition u of 0 equals u0. And then you let lambda of capital T, right? So you choose a final condition equal to, v, the vector that you want to pull back, right? If you let the final condition, if you let that final condition be true, then you solve the ODE this one going backwards. And from lambda, and the derivative is defined from lambda of t. It's some integral of lambda of t. If you want to see the whole derivation, watch the lecture. But at a high level, the way to think about it is well, with reverse mode AD, what you do again, you always solve the primal equation, right? So our primal thing was, oh, solve this ODE going forwards, right? And what you do is you take that ODE and you solve it forwards, and then what you have to do is you have to pull it backwards, right? Now, instead of doing this pullback of a static computation graph, here what we are doing is we're doing a pullback of a continuous equation, and that pullback of a continuous equation is just solving an ODE backwards in time. It's specifically solving this ODE backwards in time. So solving backwards in time basically just means that you put a minus sign in front of it. But those are details, right? But you solve an ODE going forwards, and then the pullback is to solve in reverse, where you have to use the information of your forward solve, right? So remember that so let me relate this back to the Newton method case, right? So how do you do reverse mode of the Newton's method? Well, first you go forwards, right? So you run your program for the Newton solve, and you get the x infinity from it, right? And then you pull back an operation of doing Newton's method. You could also pull back through your old Newton's method, the pulling back just one Newton's method works, right? But the key here, though, is you have to know your x0, because you're going to center your derivative calculation around the solution to your forward pass, right? And that's why you actually need to solve the Newton's method first, and then you can compute the derivative. In the same way, when doing the ODE solve, you solve your ODE first, right? And then you pull backwards, and you have to know the value of u. Why do you have to actually know the value of u? Well, because it shows up right here, right? If I actually write these little hidden t's that you never write as an ODE person, right? So this lambda is you're trying to get this whole function of lambda of t. It turns out that in order to know lambda of t prime, you actually need to compute the Jacobian of f with respect to u at the value t. So what you do then is let me. So what you do then is you solve this ODE going forwards, u of t, right? And then you take this lambda of capital T as your final condition, and you solve it backwards, right? You then solve this backwards, where at every single step of the way, you actually have to use df du, so in order to calculate the derivative of f at the point u, you have to remember this value right here. You have to be able to say, oh, u of t was this value right here, so let me use it, right? So this really kind of shows you some general principles that happens with differential programming. It looks a bit weird at first, but there's a lot of very, very general takeaways. One of them is when you do reverse mode AD of programs, you always still need to run the original program going forward. So it's always going to be more expensive than the original program, because calculating the derivative does require actually running the program first. But one of the key aspects then is that the reverse pass actually then uses the data of the forward pass in order to then calculate the derivative at the point going backwards. If you think about it from the computational graph lecture, right? As you start to go backwards to the computation graph, you're using values of like, oh yeah, I've already computed that was computed here. Oh yeah, I've used it. So every single reverse pass that you do is always using the values of the forward pass in order to calculate these derivatives, right? And then that's really the same thing as this question here, right? Why do you say y is not a function of p? Well, as you push your computation going forwards, right? You calculate y, you calculate z, you calculate the output. When you start to go backwards, you basically are saying that you're taking the derivative of each step independently, but under the assumption you're taking the derivative of each step independently under the assumption that that this is now a constant that has already been calculated. So go back through the to make that very clear, go back through the computations of the reverse of the compute graph reverse mode, and you see where that comes into play. But effectively, that's in a generalized form. That's why you're basically doing the same thing with x0 that you're now doing with u of t, right? You're just using it as you basically at every single point you need to take a vector Jacobian product. But where, what are you taking the Jacobian at? The Jacobian is a operation that's a linearization at some point, right? What is the point that you're taking the linearization at? Well, it is the place that the forward pass was at that time, right? You go forward in your compute graph, you go reverse through it as where you take those Jacobians of a nonlinear function is the Jacobian at the point that was computed from the forward pass. And so you see this in action here in a continuous space. You now solve an ODE forwards, you solve an ODE backwards. You're doing the vector Jacobian product, right? This is the VJP at every single step. But the Jacobian at that step is the Jacobian that is computed, the Jacobian of the forward ODE solution with respect to the forward ODE value at that time point. So it is a direct generalization of doing reverse mode from the continuous computation graphs to from the discrete computation graphs to the continuous ones. And now definitely going to hit time there. So if you want to kind of see the full derivation of how do you do this in a much more rigorous way, and say, go see the lecture notes and go see the video. But I like these newer forms of derivation because I feel like they're a bit more intuitive. But I do give a derivation in here, which is directly using integrals and tricks and going step by step by step, integration by parts. And what you get in the end is you get the same exact adjoint equation. So if you want to see it in more steps, doing every integration by parts, et cetera, describing every single equation, watch the video that goes along with these lecture notes here. It goes into absolute full complete detail. But there's a reason why I actually do that lecture in 2 lectures, right? So it ends up being like a 3-hour one to go through every single step of the derivation. But so takeaways for differentiable programming. If I had to summarize them, I would say that these are kind of takeaways. So the first takeaway is that sometimes the derivative of dynamic programs can be simpler than the original program. Right, and example, iterative algorithms like Newton's method. In fact, for all algorithms that iterate to 0, so complementarity solvers, nonlinear optimization solvers, and everything, for all of them, you can actually always compute the derivative in one step going backwards. That's actually a general property you can prove. So so sometimes the derivative of a different so if you think about derivatives of computer programs, sometimes the derivative is actually much different than the way that you would have computed it naively looking at the computation graph, right? The other thing is that many times the derivative of a dynamic program can be written in a way that is using the same solver, right? An example is that the derivative of an ODE solver is to solve a different ODE, right? So if you have an ODE solver, and this ends up being pretty general. So if you have this actually, if you actually think back to it, right? The trick that I showed you for how do you differentiate Newton's method is actually just to say, oh, I just have a Newton method solve. Well, the trick to derive the derivation of a root finding problem is to take Newton's method as a example of a solver for a root finding method, and then say, okay, I only have a Newton's method. How do I use a Newton method to go forward? And now, oh, I do Newton's method in reverse as well, right? Now, that Newton method in reverse actually is kind of a funky one because it's at the root already. But with the ODE case, I mean, this is another example of it, right? You start with an ODE, you derive a new ODE, and you just stick the new ODE in the solver and you get derivatives, right? So many times the derivative of a dynamic program can be written in a way so that way you're using the same solver or related solver. And this is true then for the derivative of optimization problems or optimization problem. The derivative of convex optimization gives you a convex optimization for the dual. And so you have a very nice relationship that you see all the time here. One of the next things is like the key properties of forward and reverse mode tend to hold even as you generalize, right? So the example is, forward mode AD of an ODE solver is to append the Jacobian vector product ODE and solve that going forwards, while reverse mode AD of an ODE solver is to define a new ODE of vector Jacobian products solved reverse in time, right? So if you really kind of get a feel for, forward mode AD is always pushing forward vector Jacobian vector products, and reverse mode AD is always reversing with Jacobian vector Jacobian products, right? The ODE case actually kind of just falls out of like, solving an ODE is infinitely many F applications going forwards. And so forward mode AD is just infinitely many Jacobian vector products going forwards, which is solving the ODE of the Jacobian vector product. And reverse mode AD isn't just solving infinitely many reverse vector Jacobian products going backwards, right? So you solve an ODE going backwards defined by that object. And so I think that these are kind of like three properties, which, go back through the derivations, go see the lecture that goes through all the different steps and everything. But as you tend to go through scientific machine learning, I'd say if there's one takeaway that I could give you, it's that these things tend to hold, right? So if you approach any problem and say, okay, I need to take the derivative of my PDE solver, right? Well, one thing that will show up is if it's a iterative algorithm, like say a PDE solver to a steady state, the derivative actually probably has a simple solution. You just need to figure out how to derive that simple solution. So steady state PDEs are the quintessential example of where the derivative is trivial for the same reasons, right? And now, if you have a PDE solver, you've written this very special code, or for example, you have an n-body problem, right? And you say, okay, I need to take the derivative of my n-body problem. There's probably a way so that way you just modify your n-body solver just a little bit, and now you stick a new piece of data into your n-body solver, and it will then be the n-body solver and the derivative of the n-body solver, right? So n-body solver, all these different ways that you have simulators. If you have a simulator, the derivative of your simulator is actually just a different variant on inputs to that same simulator. And then the third property is that there's always two modes of differentiation. There's forward and reverse mode, right? Forward mode is you append something to your simulator process and you just push it forward through the simulation. But there's also a reverse process where you'd have to figure out this, how do I do vector Jacobian product a step of my simulator? Right. Well, you'd have to figure out how to do the inverse of like infinitesimal time on your simulation. Not necessarily an easy thing, but if you figure out how to do that, then the reverse mode derivative process is you run your simulator forwards, and then you run this augmented simulator going backwards, and it'll give you your derivatives. And so it doesn't really matter what scientific machine learning thing you go to, whether it's neural networks or it's fancy neural networks or ODE solvers or PDE solves or all these different things. These same properties all tend to hold about the derivative. And so you can go case by case and derive it all, but keep these things in mind as a way to kind of understand what the derivation is giving you out. I think that's about what I had planned, unless you want me to really go into the ODE derivative calculation, which I think would take another hour and a half. So
and we have 4 minutes left. Thank you so much, Chris. I do have one last question to try to tie it all back to what we've done since the beginning of this class. So we started the class by saying, well, you know, the derivative operator really is just a linear operator.
Mhm.
And so could you tell us a little more, like, for example, how here it shows up? Because you know, now if to get the derivative we need to solve another nonlinear ODE, how is it still a linear operator?
Yeah, here's how I would describe it. So you have f equals f sub n circ f n minus one, right? Circ L dots circ f1, right? So this is what we said.
Mm-hmm.
Your general program is this, right? But what begins to happen when we start to talk about these, cases with, while x is less than zero, Newton's method, ODE solver, what's actually happened now is we take, we're actually just taking the case of n right arrow empty, right? So we just have essentially mathematically what we've written down when we say, mathematically what we've written down when we say, u prime equals f of upt. What we have is we have infinitely many applications of f, right? So if we go to like Newton's method or Euler's method, at the limit, right? What you basically have is you have un plus one equals un plus du times f of upt, right? Or dt, right? This infinitesimal t. So like you're doing these infinitesimal steps with f evaluations. You're just doing infinitely many of them, right?
Mm-hmm.
And so and with Newton's method, right, I said, oh, it's x infinity, right? It's running Newton's method to infinity. So what we've now basically done in this case is we say, well, we're just, we're having to take the derivative of something that mathematically is defined as having infinitely many steps.
Mm-hmm.
But even in the limit, the linearity still holds, right? And where does the linearity come into play? Well, the linearity is the fact that j equals, j n minus one, L dots, j1, right? The reason that this decomposition of operators, right? The fact that you can multiply all the Jacobians, that's equivalent to saying that the linearity property of the derivative, right? And so when we can start to say that, the vector Jacobian multiply is just to do the vector Jacobian of the first one and then multiply the output there to the second one, right? Doing this process of saying, oh, I can do the Jacobian times vector. I can do this by doing the Jacobian times vector of each function evaluation, right? That is equivalent to saying that that the derivative is a linear operator. And so
Right.
and so the fact that we get this kind of like s prime equals the Jacobian the Jacobian of the I step times times s, right? Kind of repeatedly doing this, take the output here, take it to the Jacobian, right? The fact that this ODE is really just saying, this is just the limiting process when n goes to infinity here on doing this case. So it's a very different way to think about linearity, right? But it's this linearity. Well, I mean, another way to think about it that I think is kind of a cool way to kind of get there is if you then write down u of n plus two, right? Then you have this is un plus one, this is un plus one here, right? So this is then equal to, well, let's just plug this in, right? Plus, right? If you think about it, right? And if we wanted to take the derivative with respect to this point, right? If we want to say, fraction d that dp, then we do that on this side over here, right? So ddp or ddp of this whole expression, right? And so the fact then that we say, oh, we can then push this through, right? It's the DDP of this term plus DDP of this term plus DDP of this term, right? Which is exactly equivalent to this decomposition. That is the property of linearity right there in play, right? So
Right. Right.
you just taken linearity to its infinite limit.
Yeah. Thank you, Chris. We're at time, so if you all have questions, feel free to ask, but you know, we're done for the lecture. Thank you, Chris. That
Oh,
was
thank you.
very, very insightful. So any questions from the audience? I see. Thank you for the lecture. No, I think we can wrap it up. So Chris,
cool. Yeah, and I'll reiterate that, you know, if you want to see like the full derivations of every little bit and everything, you can watch the longer version that goes along with the SciML notes. And that's probably good things. If you want to see like every integral written down with every single term, you know, every single integration by parts written, there's a video that's recorded with that. So I don't want to kind of do that again, but you know, go through the whole few hours on that, and you'll get every single step of the process.
Yeah. And it would be interesting because in the reverse mode, we've always like seeded with ones in class, but I could see that like here you seed with 0. So like interesting. It would be interesting to see looking at the notes, like
it's seeding it
how
with
you end up
the,
with that.
the Jacobian, right? So yes,
yeah, it's the Jacobian that you seed with 1, but the vector you seed with 0. I see.
Well, no, so with the
Anyways.
vector you seed it with just v, right? And so you know, but you choose a vector v that you then want to pull back the whole way. Which if it's 1, then you get the gradient, right? But if it's a vector though, then if you seed it with a basis element, right, 1, 0, 0, right, and you pull it back, you actually get the ith row of the Jacobian of your original function, right? So
yeah, we did that. We did that in last lecture.
Yeah, so so then it's funny, like in the ODE case, you're like, what is the actual thing there that's related? Well, that's the initial condition of the ODE that you pull back, right? You know, so that initial condition of the ODE that you pull back is that vector that is like that v that you're then pulling back through the whole thing, then give you Jacobian elements. Yeah.
Yeah, and also, would you choose forward versus reverse? That all depends on that product there, right?
Yeah. And in fact, in the ODE case, that I think that to me the ODE case is actually the most clear, because for the ODE case, what you can see is that let's see here. Yeah, for the ODE case, right? You know, remember that this S of t is du dp, right? So there's one value of s for every parameter, right? And so if you think of the number of ODEs that you're solving here, so the number of ODEs, right? This is you know, this is length of u plus length of u times length of p, right? Because here there's a derivative of every u with respect to p, right? So you have this scaling that is where was that?
Here.
So you have the scaling that is length of u times length of p, right? But if you think about what you do with the reverse mode, right? You solve an ODE going forwards, right? And this has, you know, length of u elements, right? You solve something going in reverse, and this actually has length of u elements, and then you do something, you do an operation that is length of p, right? And so it immediately falls that, you know, forward mode is O of you know, length of u times length of p, while reverse mode is O of length of u plus length of p.
I see.
So it kind of falls out of, you know, if you just count the number of equations, you see that operation come out.
I see. Yeah, very interesting. Okay. Well, that's all the question I had. Thank you very much, Chris. I wrap it, and I'm gonna share the Chris kindly agreed that I record the notes, so I'm gonna share with you, Chris, the recording, and also with the class, if that's okay. Is that okay? Yeah. Okay. Sounds good.
All right. Yeah. Thanks for having me.